Gosh, okay, thank you.
No problem.
So, didn't realize that. I didn't realize you had me muted. Okay. So going back to where we started. This book contains pretty much everything that you'd ever want to know, as well as it's on your website. So you can take that, and once you've got this data, then you can build applications. Until somebody sat down and worked through this data, they didn't have it. So, and it's got a complete and detailed section telling you how to read all those wonderful facts, including, let's see if I can find it here. This one right here that tells you, yes, how I know which one decays which. So there's starts, there's what you get when you get an alpha. There's starts, there's what you do when you have beta minus decay. There, that's what you get if you get a deuteron. Here's what you get if you get a beta plus out. So you give me whatever the reaction or whatever the decay is, and from that table I can find you exactly where it goes, how long it's going to live, what type of gammas I would see, how many particles I would see, so forth. So it's got a wealth of information in this. And they're relatively, by the way, the books are relatively cheap. They were built because they were built off of grants and so forth. They're not trying to make money or such on them. I think they were, I don't know if it was $12 or $15 or what have you. They're basically federal government services. But they're all on the website now. It's just you don't have a website when you take exams. And when I unplug your power, my system still works, my book. Now maybe someday they'll put them on a what do you call it, Kindle Fire, and you can play chess on the side while doing your nuclear problems. Yeah. My daughter seems to have everything on that Kindle Fire.
I want a Kindle.
So, like I said, they don't give you lambda though in the book. They give you the half-life. And like I said, lambda represents the probability of one nuclei decaying in 1 second. So we can measure lambda. That's usually what's done. You can also measure the half-life, which is how long does it take to get down to 50%. Now you can figure out what that'll be if you want. You can work out the relationship, or you might just know it if you do it a lot. So for instance, let's say you wanted to find the half-life, since that's what the book has, and from the half-life, you're going to want to calculate lambda. And they didn't give me lambda, they gave me the half-life. How are they related? Well, at t equal t1/2, A is equal to A naught over 2. That's just the definition of half-life. It's the time at which half the activity has gone away. So if you were measuring originally, say, I don't know, 20,000 disintegrations per second, 20,000 becquerels, and now you're measuring 10,000 becquerels, then you are at the half-life. So we'll put that in our equation here. We have A naught over 2 is equal to A naught e to the minus lambda t to the 1/2. We can cancel out the A naughts. And we get e to the minus lambda t to the 1/2 is equal to 1/2. Now I need to get the lambda and the t downstairs. I need to bring them down here because they're up in the exponent, so I need to take the natural log of both sides so as to get rid of the e. So if I do that, this is going to be minus the natural log of 2. Remember that when you divide, it's really the natural log, I guess if I really want to put it, it's really the natural log of 1 minus, but that's 0. When you divide, it's the same thing as subtracting logs. When you multiply the argument, it's the same as adding logs. And on the other side, you have the natural log v to the minus lambda t to the 1/2 which just makes this minus lambda t to the 1/2. We can kill the minus on both sides. That gets us this. And then it depends on which one you want to solve for. So assuming that I've looked up in the table and I've found t to the 1/2, the half-life, and I want to find lambda because I'm going to need to divide the activity by lambda to get the number of atoms, then I'm going to leave lambda alone and divide both sides by t to the 1/2. And in practicality, that's usually what's done. One measures the time to 50% of the activity is gone. That's easier than finding, 1 over e, okay? Takes the natural log of 2, which is just a number, divides by that, and gets you the lambda, which is the probability that one nuclei decays in 1 unit of time, whatever this time is. So if this is in seconds, it's 1 nuclei per second. By the way, I said seconds because that's usually what we work in. And that's usually how activity is. We talk about decays per second, not decays per century. But you could have TB centuries, in which case lambda would have the units of decays per century. Right? If it's not decay, well, either better be a lot or else find out what the hell are you looking at. I mean, that's called stable. Okay? If it takes 1,000 years before you get one decay in the table is called stable. Okay, you decay. If I put a detector around you, I will measure radioactive decay from your body. You have radioactive potassium-40, you have lots of other radioactive beans, pinto beans. Take it on against a can of pinto beans. I got detectors, they'll go off. Pinto beans are radioactive. Bananas are radioactive. Brazilian nuts. I eat walnuts this morning, they're radioactive. I'm walking around with radioactive walnuts in me. Okay? You have radioactivity. What we have to do in nuclear medicine is select an isotope that will, A, be hotter, because we want it to be very short, so that when you go home to hug your kids, you don't have the radioactivity anymore. All right, it's greatly decreased. And the second thing is it's got to be something that we can detect. Well, our detectors need to be highly sensitive to it. You can decay a lot and we only catch 1 out of every 10,000, and we're radiating your body a lot, but we're not getting a lot of imaging information. So that's another thing. We want to make good for our detectors. And last, we want to be able to separate it from all the other radioactivity your body has that we don't care about. Now, what if you have more than one radioisotope? Well, then life gets hard. There are lots of ways to try to work that. There are the expensive ways. That means you call somebody like me who has a lot of detectors and expertise, and I charge you very nice, maybe $1,500, $2,000 a day. If I'm in a good mood. If I don't like your project, it's probably going to cost you a lot more than that. All right? That may seem like a lot. That's not a lot. By the time I pay my taxes and my other stuff, that's called a good, solid rate. If you wanted to call FMC, call me on a project, they talked to a company, they expected 2 days, they wanted to charge them $100,000. Okay? Maybe there's a cheaper way. There probably are cheaper ways. If you want to work with a Geiger counter, you don't need to spend so much, assuming you know something. All right? So, first of all, you probably don't have to worry about every possible radioactive isotope in the world. You're working on a specific project. There are specific isotopes you know. For instance, the project from FMC involved using a garnet-based cutting sand to cut through a steel. It's garnet. Garnet is a well-known material. You can go onto the internet. Now, here's a good time to find the internet. You can go on it, you can look at it, you can find out where it comes from. It's been analyzed for all the isotopes that exist in it. I pull them up, it's got uranium, it's got thorium, I know exactly where the peaks should be. I calibrate a detector and take a look at it. And I start looking to see what those peaks are. I'm not just choosing the entire book. I have it very well narrowed down. Much harder when you just pick a random rock off the side of the road. Okay? Good news is we don't build random rocks in engineering applications. We build stuff. Yeah.
Oh, sorry, I put top of my head.
So, one thing that people learned a long time ago is when you deal with these guys, you don't want to plot them on a linear plot. Okay, you want to plot them on a log-log plot. And if you plot them on a semi-log plot, I shouldn't say log-log, semi-log. So So you plot the log of activity here against time. What you get is a straight line. And the human eye is really good about being able to tell if something's a straight line or not. You have stuff like this. Maybe this is your data points. Some uncertainty. That thing fits roughly that line. Now you can do a best square fit or what have you, but most times it is good enough to take a ruler. Find out whatever you want. Because the slope is directly related to the decay constant. And the activity you can read directly to find the initial activity. And that decay constant at the end is like a fingerprint. It can tell you which isotopes are there. Now you might have some data that doesn't look like this. You could have data that looks something like this. So when you get out here, it kind of looks like that. And if you look at that, you say, hey, look, you know, this kind of looks like it's going like this, and this kind of looks like it goes like that. What you have is a very short-lived isotope and a very long-lived isotope. Now, the problem is the long-lived isotope was also talking down here. So here's what we do. We go way out here where there's only one isotope left. We figure out what it is, and we figure out how many counts it was doing. And we extrapolate that back under this data, and we subtract it and replot. And we keep doing that until we're left with only one line segment. And then I found all the isotopes you have. So even if you have a more complicated problem, and there are mathematical solutions, and I'm not saying that, this is not our primary purpose. If you want to do that, take nuclear physics. We'll talk about how to deal with this in a mathematical way. But experimentally with a Geiger counter and a good spreadsheet on a PC that I got out there, I can find out a whole lot of information provided I have a good thinking brain and a good background. And I don't have to spend a lot of money. I could go and find myself a $50,000 detector and $45,000 of electronics that weighs several hundred pounds, and I could haul it out there, get myself a transformer that's got blocks all the neutral noise and make sure I've got all of the background loops in my electronics eliminated and get it isolated and tested. Or I could bring it back to my lab and put it in my $125,000 of equipment, and I could isolate the individual gammas and probably tell you what it is. But I can do this with a Geiger counter and a $2,000 PC with a detector system that I carry on my hip out to a site, okay? And I don't have to charge the same type of money, all right? So this is what's done long before we ever do the other. Use the right tool with the right brain rather than go and trying to throw technology, which is very expensive at a problem. Let me show you that this slope is related to it, although it's a pretty straightforward and simple thing. I said A is A naught e to the minus lambda t. Well, I'm going to mark this. This is this would be a single decay. If you have this, why does plotting things on semi-log paper help out? Well, when you're attacking a problem you don't know, you should plot that thing 3 times. Once on linear paper, once on semi-log, and once on log-log. We talked about as freshmen. When you do log-log, you see anything that has a power relationship. When you have things like exponentials, it'll be a straight line on semi-log. And if it's not that, and it's just a straight linear dependence, it'll be a straight line on regular paper. So I'm going to do this one. I'm going to take the log, and in this case, I'm going to take the, let's say, the natural log. If you want to take log log, you can do that too. It requires you to deal with the base change. And that would mean what you do to one side, you do the other. So that's this side. Over here, you get the natural log of A naught. Plus, you get the natural log of B to the minus lambda t. This gives you the natural log of A. Still the natural log of A naught. But the natural log of E kills the E. And so I get, minus lambda t. So if I'm plotting this, say with a natural log curve, like natural log of A versus t, that's my new y. This is my new x. So there's x. There's y. This is the value that occurs when t is 0. That's right along here. That means that's the y-intercept. We used to call that v. And this minus lambda, we'll call that m. So this is y equal mx plus b. So the slope here is minus lambda. Now, if you don't do this in terms of natural log, if you do it in terms of log, then the only thing that changes, this becomes a log, this becomes a log, but that becomes the log of e. The minus lambda t comes out front, but you have a log of e. And the log of e isn't 1. It's a number you can punch with your calculator. So the slope is slightly changed. But it's still directly related to lambda.
I have an energy question.
Huh?
If you were to see these multiple isotope decays,
Yeah.
would it make sense for the slope to always be less steep after each isotope decay? Because each...
I haven't really thought about that. Well, let me think about that. So if the slope is less steep, yes.
Energetically, that would happen. Because each one's more stable.
Which means the less probable to occur, which means that it would take longer to fall off. So the answer to your question is yes. I hadn't actually ever thought about that. I just always worked it. Correct. Because if it's going to exist longer, then it has to have a low in batting average, because it has to take a lot more at bats to get the same number of hits. Everything in the world practically can be solved either by playing baseball at a beach. Right. Beaches handle waves, baseballs handle soft particle physics and nuclear. Between the two, you've got all of it. All you need to do is just add some mathematics. Even batting average is probability, so that goes with mathematics.
Yeah.
Figure out what you work well. I don't care what subject it is. So figure out how to put a new concept in terms of concepts that you understand. I play baseball. So when I look at new concepts, I try to put them in concepts that I understand. Well, I understand baseball pretty well. I try to put them in baseballs. There are other concepts I understand pretty well. So, for instance, if I'm dealing with, I'm dealing with a new problem in mathematics, then I try to turn it into a spring problem or a mechanics problem. I know what drives you in mechanics. So if Jimmy's going to give me some bizarre weirdo problem that's in some sort of mathematics, I'm going to convert it. It was said that Feynman could always answer all the intervals off his head, determine whether they, for instance, he could determine whether a mathematical function or a postulate was true or false. And he said that his method was this. They would say, so-and-so, if so-and-so and so-and-so is true, then the following is true. And what he would do was when they said, if so-and-so is true, he would start out with, that's an orange. That's an orange with hair. That's an orange with green hair and red eyes. And then when they said, is this true, he would look to see if his green-eyed, or green-haired, red-eyed orange could do that. And if it could do that, then he'd say yes. And if it couldn't, he'd say no. But he turned it into a problem he could see, visualize. That's a key. And then you're talking about a guy who's Nobel Prize winner, one of the most creative people. If you think you can do it in your head better than he can do, I'm sorry to tell you, but that's like, I'll say, like, you're going to tell me you dunked with your feet over Michael Jordan. I ain't going to believe you. Okay, so take the problem and turn it to what you know well, so that you can take advantage of your hours of past study when you attack a new problem. All right?
So I sure relate the Pauli exclusion principle to women.
Well, that worked probably well for you, but I mean, there's almost like never, you'd also have a 0% occupancy. All right, do alpha particle decay next time. Finish reading that chapter.
Only in this class we would say something like that.
You're just a walking joke waiting to happen.
Oh man. Are we getting our test back?
Yeah, y'all want.
I don't think. Oh, go on.
I don't know if I want to judge one.
What was the average?
I didn't calculate that. It wasn't nearly as high as it's been the last 5 times previous time.
Jesus Christ.
No, if he was not taking the test, he would have done okay.
Hey, excuse me.
Yes.
We didn't get connected until halfway through the class. Did we miss any announcements?
You missed the following thing. So for the final, I'm probably looking at making a part of it a take home. Not all of it, but a part of it. The only new material on the final, which I'm going to send you guys out an email to this effect, I've sent a couple, is lasers and the stuff we're doing now in nuclear. Everything else is basically going to be stuff we already covered, so know everything on the past tests. All right, and be able to work every single problem on the past test. Other than that, no. The rest of the discussion dealt with, and I'll send you the copy of the notes that I was going through, which was reviewing what Jimmy did the previous class on decay. Because my first question was, who could tell me the physical interpretation of a decay constant? And I didn't get anybody to tell me that. So I'll send you those out. And if you have questions, I'm on Skype. Skype me.